To welcome the final speaker of this session, Sergey Bravyi from IBM, who's going to tell us about correcting coherent errors with the surface code. Thank you.
Okay, so I would like to thank organizers for inviting me here. Yes, and I will be talking about the surface code and correcting coherent errors. And this is a joint work with Robert Koenig, who is here, and Robert's students, Matthias Engelbrecht and Nolan Pert. And let me start by clarifying what I mean by coherent errors. So in my talk, I will consider this very simple model of error correction when we have ideal encoder, ideal decoder, and in the middle we have some noise, which is just a tensor product of some single qubit noise channels. And somehow there are two extreme cases of this model. So we have Pauli noise when for each qubit we randomly pick some Pauli operator, x, y, or z with some probabilities. And I'm interested in the other extreme case when each of these noise channels is just some unitary operator, u. And somehow we're interested in what happens when this unitary operator is close to identity. So this coherent noise is appropriate model for systematic errors that are caused, for example, by imprecision in our classical control and calibration. And this Pauli noise is more appropriate to model decoherence caused by unwanted interactions with the environment. Now, in the case of Pauli errors, we can do numerical simulations very efficiently using Gottesman-New theorem. But in the case of coherent errors, basically we have to consider, we have to do exact simulations, and the brute force algorithm requires time growing exponentially with the number of qubits. So it's very inefficient. And recently, David Pulin and Dharma Van proposed more efficient algorithm based on tensor network contractions, but it still have time growing exponentially, although now it's exponential in the square root of n. So what we would like to do is to achieve simulation time polynomial in n. Also, we would like to estimate error thresholds for such coherent noise. And previous work mostly focused on concatenation of small chords. This is precisely for the reason that numerical simulation for coherent errors is very hard. For example, people looked at concatenation of Steen chord and one-dimensional repetition chords, but we don't have reliable threshold estimates for topological chords, like surface chord or color chord. And finally, we would like, say, even if we are below the threshold, then error correction is not perfect, so we still have some residual logical errors, and we would like to understand somehow the structure of these errors. For example, we can ask if our physical level noise is coherent, is it true that logical level noise can be well approximated by random Pauli errors? And so people from Ken Brown's group studied this question for 7-qubit Steen chord, but it's hard to say how these results can be generalized to topological chords with large distance. And this may have important implications on which metric we choose to quantify our logical error rates. For example, we could use average fidelity, or we could use diamond norm distance from identity channel. And depending on the degree of coherence, these different metrics can vary significantly. Okay. So now let me briefly discuss how we can model noise at the logical level. And in this talk, I will only consider decoders that work by measuring code syndrome, and then they apply some Pauli correction depending on the measured syndrome. And now there are two choices that we can make. For example, we can somehow trace out the measured syndrome after we applied Pauli correction. And then we look at our final logical state, which is averaged over all measured syndromes. And this defines a logical channel. Somehow, if we have a single logical qubit, this is just a single qubit channel. So it has a very compact representation. It's basically a 4x4 matrix. But this model is, I think, more appropriate for quantum communication theory than somehow adversary is confined to this noise box. And for quantum fault tolerance, it's probably more appropriate to consider this model than the syndrome, measured syndrome is included in the output of our logical channel. The point is that if our noise is non-Markovian or gate dependent, then subsequent errors can correlate themselves with the measured syndrome, and this can help the environment to distinguish different logical states. And of course, the number of different syndromes can be exponentially big. So this logical channel does not have a concise description. But if you look at some particular syndrome, we can still describe this logical channel by a small matrix. And so simulation tasks that I'm interested in is to sample measured syndrome from the respective probability distribution. And then for a given syndrome, we would like to compute this final logical state condition on the measured syndrome. And so in this talk, I will only consider surface codes. So you have already seen this in Cody talks. We have physical qubits at sides of the lattice, X stabilizers at black plaquettes, and Z stabilizers at white plaquettes. And logical operators correspond to vertical and horizontal strings of X and Z. And so our first result is a simulation algorithm for coherent errors of this form. Then on each qubit, we apply Z rotation with some fixed angle theta. So what we are going to simulate is the following protocol. We start from some initial logical state encoded by the surface code. We apply bitwise Z rotation. Then we measure the syndrome. So P sub S is syndrome projector. Then we run our decoding algorithm, say minimum weight matching, calculate Pauli correction operator, and it brings us back to the code space. So we end up with some final logical state. The input of our algorithm is code distance with Z rotation angle theta and initial logical state. And the algorithm outputs measured syndrome and final logical state conditioned on the syndrome. And the runtime of this algorithm scales polynomially with the code distance, as shown here. Basically, it's d to the fifth power. And I will show you some numerical results later on. Now, we cannot simulate general coherent errors described by SQ2 operators, but we can simulate certain, we have some partial results for simulating logical state preparation. So as you well know, the surface code allows us to prepare logical X or logical Z basis states fault tolerantly. And for example, we can initialize each physical qubit in plus state, measure the syndrome, apply some Pauli correction, and this will give us logical X basis state. And we can simulate a noisy version of this protocol. Then somehow we have coherent errors in preparing this initial product state. So instead of initializing each qubit in plus, we initialize each qubit in some state psi, which can be completely arbitrary. So again, given code distance and this initial state psi, we would like to sample syndrome from the corresponding probability distribution and compute the final logical state. And in this case, the runtime of our algorithm is d to the fourth. So it's slightly better than for error correction. Now, let me sketch how this algorithm works. And the key ingredient is a mapping of the surface code to a system of Majorana fermions. And a specific mapping that we use was proposed in this paper by Wen. And it's closely related to Kitaev's honeycomb model, but also can be described by Majorana fermions. And this mapping was later used by Barbara Terhal, Hessler, and De Vincenzo to construct some realistic Hamiltonians with topologically ordered ground states. So this is my plan for the rest of the talk. I will give you some background on Majorana fermions and fermionic Gaussian states. Then I will show you this Majorana representation of the surface code and explain how our simulation algorithms work. Okay, so I'm going to consider Majorana operators, Majorana fermions in terms of qubits. So if we have a system of n qubits, this is essentially the same as a system of 2n Majorana modes. And for each Majorana mode can be described by this operator C, which are certain products of Pauli operators. And I guess my notation is different from notations of Accorded talk. So he used gammas instead of C. So these Majorana operators obey these commutation rules. And any n-qubit operator can be expressed as linear combination of these Majorana monomials. So they form a basis for operator algebra. Now, suppose we have some n-qubit normalized state phi. Then we can define this covariance matrix M that basically tells us what are expectation values of two-mode Majorana operators. Now, Majorana commutation rules imply that this operator is Hermitian. So this is a real antisymmetric matrix of size 2 to the n, sorry, 2 times n. For example, if we have just single qubit and we consider this zero state, then its covariance matrix would be like shown here. And we say that n-qubit state is Gaussian if it obeys fermionic Wick's theorem. So what it means is that we can compute these Majorana correlators using this formula. Say in the case of fourth order correlators, we consider all possible ways to group these Majorana modes into pairs. And then we take product of two-mode correlators over all these pairs. And because these are fermions, there are plus minus signs here. And this sign is basically controlled by parity of the permutation that brings us from this order to this order. And in my talk, I will only need this Fick's theorem for a fourth order correlator, but it can be defined for higher order correlators as well. Now, what is important is that this covariance matrix provides a full description of a Gaussian state. To describe such state, we need only n squared real parameters, as opposed to 2 to the n for general n-qubit states. Now, let me describe some basic facts concerning these fermionic Gaussian states. First of all, if we have a pair of Gaussian states phi1, phi2, then the tensor product is also a Gaussian state, and its covariance matrix is just a direct sum of covariance matrices of phi1 and phi2. Secondly, if we have a small number of modes, then essentially any state is Gaussian. So more precisely, if we have a 2-qubit state, which is eigenvector of this total parity operator, then such state is always Gaussian. And finally, so there are certain operators that have a nice property that they map Gaussian states to Gaussian states. In particular, so one important example is this 2-mode parity projector. So this operator ICPCQ is a Hermitian-Pauli operator. So this is projector onto eigenvalue +1 for this Pauli operator. So our algorithms work by simulating a sequence of 2-mode parity projectors. And these measurements start from some simple initial Gaussian states. And so this is a typical step of our algorithm. So we have some Gaussian state phi, and we know its covariance matrix M. And then we apply this parity projector. We get some other Gaussian state phi prime. And our job is to compute this new covariance matrix M prime. And first of all, we can easily compute normalization of this new state. So this normalization is basically given by this matrix element of the covariance matrix. To update the covariance matrix, we have to compute expectation value of this operator on phi prime. So it means that we get expectation value of this operator on phi. And this is a linear combination of Majorana monomials of order 2, 4, and 6. And actually, the monomial of order 6 can be simplified because we can commute CP from the right to the left and cancel CP over here. So we only get monomials of degree 2 and 4. So we know how to compute them using Fick's theorem. So the important point is that updating the covariance matrix is very simple, and it takes time roughly n squared. So now let me move on to this Majorana description of the surface code, and I will only show you pictures for distance 3. So we start from this surface code, and then we replace each vertex of the lattice by 4 Majorana operators that are shown by these blue dots. So now we have 4n Majorana fermions. And I'm going to choose a particular orientation on every edge of the lattice. Using this orientation, I can define these edge operators, which are just 2-mode Majorana operators. Now, if you look at this picture, you can see that all H operators are disjoint. So they act on different pairs of Majorana modes. And then somehow this implies that all H operators pairwise commute. So we are going to use this strategy for simulating syndrome measurements of the surface code. So we would like to express each plaquette stabilizer of the surface code as a product of these H operators. And because H operators pairwise commute, we can first measure syndromes for each H operator, and then classically compute syndromes for plaquette operators. Measuring syndromes of H operators is easier because these are just two-mode parity measurements that I just showed you. And to explain how this works, I need to define one extra code. And again, you have already seen this in a code talk. So this is essentially a Majorana version of the well-known C4 code from newspaper. And here we encode one qubit into a system of 4 Majorana modes. And we have only one stabilizer shown here. And we can choose logical operators as two-mode Majorana operators. Say this is our logical X, logical Y, and logical Z. Now, for each logical operators, you have two choices how you pick this pair. And I'm going to use this freedom somehow later on. So you can check that these operators indeed commute with the stabilizers and anti-commute with each other. And another property of this code that will be important for me is that any logical state of this code is a Gaussian state. And furthermore, logical operators, well, I don't think I will need this property, actually. Now, I would like to represent plaquette operators as products of these H operators. And the first step is to encode each qubit of the surface code using this Majorana C4 code. So now, instead of single qubit at each vertex, I have 4 Majorana fermions, and the encoded plaquette operator looks like shown here. Now, it's a minor detail, but you have to choose particular ordering of Majorana modes at each C4 code. But if you choose the ordering properly, then what you get is shown here. So this is our encoded plaquette operator. Now, let's look at the product of all H operators that live on the boundary of this plaquette. So I call them A1, A2, A3, A4. And if you take a product of all these H operators, they include every Majorana mode located on the boundary of the plaquette. And this is the same as encoded version of plaquette operator. Now, again, you must be careful how we choose orientations of these edges, but with some minor details. And of course, we have the same representation for X-type plaquette operators. And so to simulate syndrome measurements, somehow we have to follow these steps. So we want to measure syndromes of surface code stabilizers on some initial product state. Now we encode each qubit using C4 code. Now we have to measure syndromes of encoded plaquette stabilizers on encoded product state. As I said, it suffices to measure syndromes of H operators. And we know that this encoded product state is Gaussian because I told you that any logical state of C4 code is Gaussian. So somehow all we need to do is to simulate a sequence of two-mode parity measurements starting from a simple Gaussian state. And we know how to do this efficiently. Yes, so if you implement this algorithm naively, the overall runtime scales as n cube. And we can improve the runtime a little bit by choosing a particular order in which we measure these H operators. For example, suppose I measure these operators column by column, and I move from the left to the right. And consider what happens at some intermediate step. So all my runner modes in this left region have been already measured, and all my runner modes in this region on the right are grouped into this C4 encoded single qubit states. And there is this active zone in the middle, and it includes C4 encoded single qubit states in which one or more modes have been measured. So basically, if you look at this state, you have unentangled modes on the left and on the right, and some entangled state for this active zone. Okay. And so in our simulation algorithm, we only need a covariance matrix to describe the state of this active zone. And because this zone has thickness, has some constant thickness, somehow we can improve the simulation runtime from n cubed to n squared. And so this shows how to simulate syndrome measurements. Now, the next thing we want to do is to compute the final logical state conditioned on the measured syndrome. And so suppose we have already measured all these H operators. Then you can notice that there are 4 Majorana modes located at the corners of the lattice. And these modes do not belong to any H operator. So it means that somehow these modes remained unmeasured. And one nice property one can check is that the reduced state of these 4 corner modes is actually the final logical state which is encoded by fermionic C4 code. So if you want to compute the logical block vector for this final logical state, all we need to do is to compute expectation values for these Pauli logical operators, like C1, C2, C2, C4, and so on. And these expectation values can be read off from the covariance matrix of the final state. So this basically all about this simulation algorithm. And now we implemented the algorithm in C, and let me show you some numerical results. So for numerical simulations, we chosen the initial product state of this form. So it lies on the equator of the block sphere, and we have this rotation angle theta. So what should we expect to see? So if theta equals 0, then this is ideal protocol. So we always get our final state is always logical plus. Now, if we pick theta equals to pi over 4, it means that our initial product state is basis state of y basis. And basically, one can easily check that in this case, the final state is always logical, is always eigenvector of logical y. So in this case, we never get the desired logical state. But somehow this point is, here we don't expect fault tolerance because the measured syndromes are essentially random. Yes, so we expect that the error threshold lies somewhere between 0 and pi over 4. And so the quantity that we computed numerically is logical error rate that I define by this formula. We just compute the distance between our final state and desired logical state, and we average over syndromes. And in numerics, we compute this average by Monte Carlo. And so these are results that we got. Here I show you data for distance between 9 and 49. And each data point corresponds to averaging over 50,000 samples, syndrome samples. And you can see that all these curves intersect at some point, which is close to somewhere 0.13. Yeah, so this is our estimate of the error threshold. And actually, this value is very close to pi over 8. And if we pick theta equals to pi over 8, this means that our initial state is a product of magic states. So a natural conjecture would be that this is actually the error threshold. Now, if you look at this region below the threshold, you can plot the same data using log scale. And as expected, as you increase code distance, the logical error rate decreases exponentially. So these are the same data, but the horizontal axis is the code distance. Now, let me move on to simulating error correction when our initial state is some logical state. And the algorithm mostly follows the same strategy. So we use this Majorana representation. And we reduced syndrome measurements to simulating a sequence of two-mode Majorana measurements. So I will only highlight somehow the differences between these algorithms. And first of all, let's try to understand the structure of this logical channel after error correction. And in this part, I will only consider coherent errors that have this form. So our algorithm works only for Z-type rotations. So we start from some initial logical state. We apply this coherent Z-rotation error. And then we measure the syndrome. So this determines syndrome probability distribution. It turns out that this syndrome probability distribution does not depend on our initial logical state. Another nice property is that somehow the logical channel conditioned on the syndrome is just logical Z-rotation by some angle theta that depends on the syndrome. And I will refer to this angle theta of S as a logical rotation angle. Now, let me briefly sketch how the proof goes. By definition, our Pauli correction operator must bring us back to a chord space. So whatever decoder we use, we must have this property. Somehow, if we use this identity, we can rewrite our final logical state in this form. And now, let's look at this operator. So it's sandwiched between two projectors onto the chord space. And this operator is a product of Z rotations. And our correction operator, which we can assume is Z-type Pauli. So we can always expand this operator in the Pauli basis. And the only operators that contribute to this sandwich operator are stabilizers and logical operators of the surface code. And we use the fact that Z-type stabilizers of the surface code have even weight, whereas logical Z-type operators have odd weight. And somehow using this fact, you can check that indeed this, if you sandwich this operator between code space projectors, you get some Z-type logical rotation. And the normalizing coefficient here determines the syndrome probability. So there is nothing special about surface code here except for this fact that these stabilizers must have even weight. Now I'm going to define logical error rate using this equation. And this is basically the average diamond norm distance between our logical channel and the identity channel. So this is the reason for putting this factor of 2 here. And we used the minimum weight matching decoder to compute Pauli corrections. And in this decoder, all the weights, we set all the weights equal to 1. So the decoder does not depend on Z rotation angle theta. And if we allow decoder to depend on theta, then in some sense this is cheating, because optimal decoding strategy would be just to undo all rotations. But if we insist on having decoder independent of theta, then somehow the problem becomes non-trivial. And so these are numerical results that we got. So this algorithm is slightly less efficient, so we can go only up to distance 25. And again, all these curves intersect roughly in 1 point, which is close to 10% times pi. And so interestingly, so this threshold estimate agrees very well with what one could get from applying Pauli twirl approximation to our physical level noise. So if you twirl Z rotation with angle theta, you get random Z errors with rate equal to sine squared theta. And we know that for random Z errors, the surface code has error threshold roughly 11%. And this agrees with the value that I showed here. Now, again, these are the same data shown using log scale. And in this region below the threshold, we have exponential decay of logical error rate as we increase the code distance. Now, here is something more interesting. I told you that for each syndrome, we have some logical rotation angle, theta of S. And we can ask what is probability distribution of this logical rotation angle. And this is what's shown on these plots. So here I consider a regime below the threshold. So for most of the syndromes, error correction is successful, and a logical rotation angle is 0 or very close to 0. So actually, these plots have a delta function located at theta equals 0. But to make them more readable, I just remove this delta function. So you can see that on both plots, we have this peak in the middle, and this peak located at logical rotation angle pi over 2, which correspond to Pauli logical Z error. And as you can see, if we go from small distance to large distance, somehow most of the weight comes into this peak located at pi over 2, which means that increasing the code distance make logical level noise closer to random Pauli errors. So if you have just, if you would only have random Pauli errors, then all the weight on this plot would be concentrated in this central peak. Now suppose we want to quantify how coherent is our logical level noise. Well, there could be many ways to do this, but suppose we define this two different logical channels. So the full channel just applies with logical Z rotation, and the twirled logical channel is obtained from the full channel by applying Pauli twirling. So basically, we disregard all coherent component of our logical noise. And now we can define two different logical error rates, one for the full logical channel and one for the twirled logical channel. So this is just the average diamond norm distance between the logical channel and identity. And I'm going to use the ratio between these two logical error rates to quantify how coherent is our logical noise. So this ratio is always greater or equal than 1, and it's equal to 1 if and only if the logical noise describes random Pauli errors. And here I plot this ratio for different code distances and for different physical Z rotation angles. So as you can see that, again, increasing the code distance makes logical noise less coherent. So this ratio moves closer to 1. We can somehow we can do the same simulation for the average logical channel that I defined in the very beginning. Remember that for average logical channel, we trace out syndromes measured by the decoder. And here the story is similar, but as we increase the code distance, it appears that the logical channel becomes exactly a random Pauli noise. So it's natural to conjecture that in the limit of infinite code distances, the logical channel has no coherent part. And this is basically all I have to say. So to conclude, I showed you efficient simulation algorithm for error correction with coherent errors in the surface code, and we estimated error thresholds, and we observed that increasing the code distance indeed makes logical level noise less coherent. And thank you.
Thank you. Are there any questions? I guess Steve is first.
Hi, Sergey. Wonderful talk. Andrew Doherty and I and our student Eric Huang have a sketch proof of your conjecture at the end.
Oh,
there. That
interesting.
Yeah, so maybe we can talk about it a little bit later. So it's true.
Okay, so it's no longer a conjecture.
Well, it's sketch proof, so, you know, put a little asterisk on that. I think there's still work to be done filling in the details, but we're quite confident that it's true, and we have an idea of how to prove it. We've not sat down and tried to pin down the details yet, but I can certainly see a path to a complete proof.
Okay, I would like to hear about that.
So it's really a nice technique for establishing what's going on with coherent errors within the limits that you've described. Any chance that you might make this available to the community? Because it seems pretty complicated to actually implement at the software level.
Yes, I mean, if my co-authors don't mind, we would be happy to share the simulation code. So as I said, it's a C++ code. So the present version is not very readable, but hopefully this will improve.
Any more questions? I can see one right over there. I'll come over there in a moment. Any more on this side of the room? Last one on this side of the room.
You had this for the surface code, and it looked like that was important in the construction. Can it be generalized to a broader class of stabilizer codes?
I don't think so, because at least for our
Steve
algorithm,
thinks
it's important that somehow if you map your stabilizer code to my runner code, you can measure syndromes using only 2 mode my runner measurements. And my feeling is that this is a special feature of the surface code. But I'm not sure.
I'll move over to the other side of the room. So any questions on this side of the room? Ben.
So in decoding, you end up doing a syndrome-dependent Pauli. But if the noise is coherent, you might think that there's some other angle that you would want to rotate by depending on what syndrome you observed. Did you try this? Did you see any success with this?
Basically, we only allowed decoder to apply Pauli corrections, and yeah, we have not thought about like more general correction operators. As I said, if the decoder has information about this rotation angle theta, then the optimal decoding strategy is just undo the rotation. But if you have some partial information, I would imagine that there is something you can do beyond just Pauli corrections. But we have not thought about this.
Maybe time for one more question.
For simulating syndrome extraction, you said naively the time would take order n cubed, but if you think carefully about the sequence you do, you can bring it down to order n squared. We know that for general stabilizer codes from the Gottesman-Nil theorem that naively you can simulate syndrome extraction in order n cubed, but Gottesman and Aronson showed us you can do it in order n squared. But even further still, Anders and Briegel showed us that you can do it with the graph-type representation. You can do it even faster for sparse codes like the surface code. And I was wondering if you're able to exploit the sparsity of the code somehow to improve even further beyond this n squared. I know they're kind of apples and oranges a little bit because one's for general stabilizer codes and you've already used a lot of the structure of the surface code to get this Majorana simulation. But I was wondering if there are any other tricks with sparsity to be had.
Yeah, so our algorithm certainly exploits sparsity of stabilizers of the surface code. Now, if you go to graph state representation, I'm not sure that the graph is actually sparse because
it's only log sparse. It's true, it's not like strictly sparse, but sparser than a generic stabilizer simulation.
Yeah, so I don't see any obstacles to improving the runtime beyond n squared, but we thought about this, but it seems hard to get further improvement, at least using this approach.
Okay, thank you.
Okay, so that brings this morning's session to an end. It's now time for lunch, but before we go, let's